That's footage.
Because I had to do.
I didn't even see an integral, so that's crazy.
I had to do a bar chart and a bar chart.
On the quiz?
On the quiz?
That doesn't sound right.
Because I wanted to see if it absolutely converged.
Yeah, you had a lot of work going on there. I was
But I could have just used the ratio.
Alright guys,
I was scared of your paper.
Adam, which one again?
Oh shoot, I just got out
You
of it.
said 30.
30?
Yeah, it was question 30.
11-8?
And after that,
Yeah. It wasn't like a conceptual one or anything. I was just asking, I mean, if I could, I just lost my book. Okay, there we go.
So, real quick, something that relates to that. So here's a general power series, right? They're talking about one specifically built around 0, I think, if I remember correctly.
Yes.
Yeah. This will have a radius convergence centered at what? What will this converge for no matter what? I don't even tell you what that is. There's a specific value of x this will converge for no matter what.
0.
0. If I make x 0, isn't this adding 0 forever?
Yep.
Okay. So this has a center of 0, and then it's going to go out. If it goes out at all in one direction, it goes the same amount in the other. And that's because of the absolute value nature in the absolute value of x, and you split it up into an inequality with both sides. It's because of that, right? So this problem, is this the problem about 4 and 6?
Yeah.
Okay. So it tells me that I have something like this, and it converges for x equal -4. But it diverges for x equals 6. What is the biggest that the radius convergence could be? I don't even know if that's that they ask you, I don't care. 5.
could be fine.
It's possibly.
Oh, for the following series. All right. So for this in itself, no. The biggest the radius convergence could be is 6.
Oh yeah.
Wait,
I just
why
wouldn't
did you start
include
with
6.
Yeah,
So the biggest it could be is this. I just wouldn't include 6. What's the smallest it could be?
-4.
Yeah, -4. 4. Right.
What?
What's up? What's the matter?
Are these not a range of numbers? What is the smallest it could get? -4, and the largest it can get 6.
Okay. The radius of convergence is centered at 0.
Oh,
it
okay.
converges at -4, but it diverges at 6. If that's all I know, then this is the smallest it could be, and this is the biggest it could be.
Those aren't limits. That's a range that you're given.
Yes.
Okay.
Yes. Okay.
And
So
why
now,
did-
sorry.
I was gonna say, why do we know that the center of the radius is 0? Or the radius?
Because this has not been shifted.
I think that's good.
I really want this to make sense. No matter what will this converge for if x is 0?
So is our center radius always A?
Yes.
Oh,
Yes. There you go.
My question wasn't really conceptual like
Sure,
that.
sure.
My question was, I don't really like. There's not much work to show for that, right? I like explain at the end why like this works like it does, but like when you have just Cn, that means x is 1. That's
Yes,
inside
yes.
the radius converges.
Yes.
It converges.
Yes.
Yeah. Okay.
So, I mean, this goes on to say something like this. What if you know this converges, all right, I really want this, let me take away this extra stuff.
And they don't give you any complicated values, so
It
it's like
converges for -4, which means at least converges here, right? And it diverges at 6, which means that most diverges there. What can you say about, let's just do one of these, this?
it converges.
I know you've done it, I know you just said the answer, nobody heard you, that's okay, so I'm gonna ask that. What can you say about this?
it converges.
Why?
Because x is to the power of 0, and since the A of n.
What do you mean x is to the power of 0? What do you
Well,
mean?
the x, it's not there, so there's no like power series.
No, what's the value of x? This is from this.
1.
The value of
Oh,
x
yeah.
is 1.
Yeah.
If the value of x is 1, does it converge?
Yeah.
Yes, we just identified. If it converges at -4, it must converge also up at 4. It's got to converge across this whole thing. The center will be at A. In this case, A is 0. and then it's going to work its way out from there.
I'm a little bit confused. So wait, I thought that without an A, I mean,
The center is 0.
The center is 0.
I mean, there's always an A.
Yeah.
If you
but
make
in
it
this
0,
case,
then
A
it
is
looks like this.
Okay.
Yeah.
And how does that relate to our A problem?
So, if the center is 0, and I know it converges at -4, right? Then it must go to 4 at least. It could go all the way to 6. It diverges at 6, but it could be that it goes all the way up to 6.
Okay.
Just not including 6.
Yeah.
So they asked me this means x is 1, that's in the area of the interval of convergence, so that would converge.
I got you.
Yeah, if they put a 7 to the end, what would that mean?
Divergent.
It's outside,
Yeah.
it's definitely divergent then, yeah. So that's just kind of a direct question about the interval of convergence, what could it be and what does it mean, right? Maybe. Yes?
So if we were to get a question like this, and they gave us like a value that falls in between what we know.
Oh yeah, that would be evil. So,
So
if they ask you about 5, which I don't think they do,
they don't.
yeah, that would be remarkably evil. Because from what they told us, what can I say about this? I can say exactly nothing about that.
I could say it may or may not.
It may or may not. So that's what I could say. I could say, I don't know. If they give me a 3, converges. If they give me an 8, diverges. They give me something in between 4 and 6, I don't know how big this is. I just know it's got to at least include -4. I don't know. I know it has to include -4, but stop right before 6. That's all I know. So 5, I don't know. But 3, yes. 8, no. I know those for sure. So if they gave me something in the middle, that would be a little evil. Because they would be implying you should be able to give an answer, and you can't. Okay. I know we just did this last time, and last time seems like 3.7 billion years ago. I know. Wednesday to Monday is a huge gap. I know that. Let's do an example problem, not conceptual like this, just to kind of get back in the groove.
Can we do number 18?
Sure. Okay. Maybe you can help me out, read that out to me.
That's gonna be,
Square root of n
yeah.
over 8 to the power of n, and then times x plus 6 to the n.
So what's the center of the interval? Gonna be
6.
6 or -6.
There it is.
6, sorry.
What guarantees convergence is if this is 0. -6 makes it 0, that's the center. And maybe this allows more stuff to work. Maybe. That's the idea. Because n is going to infinity, so maybe this thing allows more things to work. Okay, maybe. Okay. So what do you do?
Ratio test.
Ratio test. What's it, what do I put?
It's gonna be root n plus 1.
N plus 1, good, everything's n plus 1, right? Times,
8 to the n over root n x plus 6.
okay. Okay, let's see. So I got root n plus 1 over root n, I really can't do much with. So just gonna collect those. I lose n of these, is that cool? So I have one of those left. I lose n of these, so I have one of those left. And what's the limit as n goes to infinity of this?
1.
1. So then I get, the answer is x plus 6 over 8. And that, so I really want this to make nothing but sense. Ratio test is related to geometric, where the limit of the ratio comes out to be r. It's one element divided by the one before it. That's what r is. What's got to be true about r, what's got to be true about what we get, it's got to be less than 1. So you immediately say less than 1. I mean, you impose, You say, in order for you to work, you gotta be less than 1. If I solve for x, I get all the values that work. What's the very first thing I do here?
Multiply by 8.
Multiply by 8, and then I can see verify my center is at 6. And then how do I rewrite this?
It's going to be negative 8 and the greater than sign.
Yeah, x plus 6 between negative 8 and 8. And only if you want this to be less than 8, it can't be negative 9. The inside can't be negative 9, right? Absolute value 9, that's bigger than 8. Shit, so it can only go down to negative 8 and up to 8 in order to stay a size less than 8. And then, of course, you just
Add 6 to this, or subtract 6.
I just did a whole prompt for you, damn it. I get excited. I want to know what the answer is. So am I done? I didn't really do a whole problem, did I? I didn't really finish this yet. What do I still have to do?
Check the endpoints.
So in this case, we have determined that more than just negative 6 is a guarantee. Guaranteed to make this converge. And again, trivially, if you make everything 0, it adds up to be infinite. Ooh, it's amazing. Do you guys get that?
Yeah.
That part is like, all right, big deal. What's really neat is when the other shit allows other things to work too. I want you to realize, why does that kind of make sense? Because this 8 to the n, what would go here to make this a nice geometric, like 7 would work, right? So x equal 1 should work. You with me? 7.5, why would 7.5 work? If I put a 7.5 here, isn't that 7.5 over 8 to the n? Isn't that geometric? Isn't the square root of n growing so slowly I can just ignore it? Maybe. And again, that's not good enough to kind of like, we do the work and we go, why does that make sense? Oh, because this wants to be geometric. And as long as this is less than 8, r is going to be less than 1. Now, we do have to plug in the endpoints just to see if anything freaky happens. So you do have to let this be negative 14. Right? But, all right, so I'm at least going to leave something for you to do. Maybe. Or do you want to? So if you so now you have to check the endpoints.
R equals 8 for this, right?
Yeah.
Okay.
Equals 8.
Yeah.
Oh.
So let x equal negative 14. What does my summation become now? If x is negative 14, what do I get here?
Negative 8 to the end. Negative 8 to the end.
So I get negative 1 to the n, square root of n. Is that cool? Because the 8 to the n's cancel.
What's my divergence?
Does that converge or diverge?
I diverge.
Because the limit is n goes to infinity. Same thing's going to happen when I put a 2 in there, right? So that one's pretty quick. So do I need to include the endpoints?
No.
No, because that makes it diverge. My answer should be everywhere this converges. If I make n, like I said, if I make n negative 3, or x, sorry, I keep saying n, shit, I'm sorry. If I make x negative 3, right? Don't I get 3 over 8 to the end? Isn't that convergent geometric series? Now the part that the square root of n grows so slowly compared to a number to the n power. It grows so slowly that it actually does nothing overall to the, whether or not this thing converges or not. We don't necessarily really, I just told it to you, but do you really understand why? Not totally, but if you do enough of these problems, you start to realize, oh, okay, so it grows so slowly compared to 8 to the n and 3 to the n. It doesn't really change things. Okay. Anything else, guys? Nothing else, okay. Yeah, that makes me a little concerned. There's some really freaky ones in there. Okay. Let's see. Yeah. Okay, so that's basically how they all work. So your last two things are always check the endpoints. And the endpoints, one could work, both could work, neither could work, any of those could happen. So don't start to make guesses about what's going to happen. You just got to set it up and look at it. All right. Really, I just desperately want you guys. All right. This is really kind of nifty because now, and again, I think I told you this. If I am a teacher, I am, and I want to make a test and I want to have the answer be convergent, it'd be nice to know, okay, what number could I put here so that it makes this convergent, right? So that's a really lame example of what this is doing, but it kind of is telling us what number could I put there and the resultant would be convergent. Okay, maybe. Now, okay, we're finally, okay. All right, so I'm gonna let you guys get into that. 11.9, we did a little bit of 11.9. Let's do this. The only thing 11.9 tells us is something we already knew. So we're like, thanks 11.9. We knew this from before. It's one of the first things it tells us. Does anyone remember where this came from? Yeah, a over 1 minus r, where specifically this is 1 plus r squared. So sure enough, it's a geometric. Aren't you multiplying by x each time? So x is acting like r. The first term is 1. The r is x. Old news. But now we are looking at it as a function equals a polynomial. A completely not polynomial function equals a polynomial function.
This is 11.9.
Yes. Now, somebody help me out. What is the integral of this?
Natural log of 1 minus x.
Negative.
Or negative natural log of 1 minus x.
So natural log of 1 minus x.
Am I true?
It's negative.
Yeah.
Or it's negative.
Negative because of this, right? So it'd be 1 over 1, if you take the derivative of this, 1 over 1 minus x times the derivative of the inside. So you need a negative there. Okay. What's the integral of this?
X.
Yeah, so x plus integral of this. So I'm just going to integrate the sign, right?
1/2 x squared.
1/2 x squared plus
X cubed over 3.
x cubed over 3. I like it. Carmen comes in with a different format. What do you get when you integrate this?
X the n plus 1 over n plus 1.
And now let's see, let's make sure this is going to work. If I let n equal 0, do I get this?
Yes.
Yes, I do. If n is 0, I get x to the first over 0 plus 1, I get x.
Yep.
Sweet. We just took this that we did not create. We didn't make it. We just know it from, we proved it from geometric series. I didn't give it to you as a power series. It was just geometric series. That's all it was. But now that we know this, I can take a derivative of this. I can take integrals of this. And I can create new, so that's the power series for this function right there. And what that really, really means is if I put a number in here that is close to 0, these should match up pretty quickly.
What about when you like get a really big number? What happens?
Oh, something far away from 0?
Yeah.
So okay. So if you do the radius of convergence test, right? I don't remember if we did it on that yet or not, right? The really nice thing, 2 things. The radius of convergence will in itself tell you how far from 0 you can go, right? But more importantly, it tells you when the infinite polynomial works,
Oh.
right? I want this to make sense. So let's just look at this right now. This, for values of x close to 0, is given by this infinite polynomial. Okay, and let's kind of, let's do two things. Okay. I'm gonna erase this for right now. I just wanna work at this guy. It's a little bit easier to look at.
When you say like it's gonna tell you when the infinite polynomial works, you mean like to which degree it's gonna work?
No. So, let's do this. Let's figure out the radius of convergence for this, just by itself. All right, so looking at this guy, this will be nice and quick. So it'll be x to the n plus 1 divided by x to the n, right? The limit and goes to infinity. This is equal to, I lose, so I just left with x, correct?
Yeah.
Less than 1, so the radius of convergence is that. And then if I put a negative 1 in for x, that's negative 1 to the n is just negative 1, 1, negative 1, 1, negative 1, 1. No, and if I put a 1 in, it's just 1, add that forever, infinite. Is that, you guys with me on that so far? This one's a beautiful one. I mean, this is just so quick. Okay. What that means is if x is anything between these two, this infinite polynomial will give you the exact answer to this. So, does this work at all if x is 3? Doesn't work at all if x is 3. Will not work at all. Will I need fewer terms if x is close to 0 to make a decent approximation? Yes. Do you guys remember linear approximation? Shit, somebody's telling me they don't. Tell me honestly, how many of you guys don't remember a linear approximation? Okay, very quickly. Okay, good. Because I'm going to reference linear approximation a few times. Let's talk about linear approximation first. In fact, let's do it for this. I want to show you something kind of nifty. If this is my function, and the funny thing about linear approximation, what is the formula for a line that isn't mx plus b? I'll get it started.
Slope times x minus x1.
All right. Hopefully that's sort of coming up from the back of your brain somewhere. Okay, I like it. For a given function, if I am interested in 0, I want to go around 0. Isn't that what this is built around? This is built around 0, yes? That's it. This x minus a is 0. y1, so this will be x1. I'm building this around 0. So just let me show you in general. If I'm building it around a, I really want this to make sense. Y is the output. So in general, if I'm going around a, this is my very quick linear approximation lecture out of nowhere. If I'm building it around a, y1 is going to be the output at a. Right, so I'm just adding it over. What's the slope at a? Well, what's the slope at a?
The derivative.
The derivative at a. X minus, and the input is a. You guys with me? So if a is 0, y is f of 0 plus f prime at 0 times x minus 0. Is that cool? Okay. The conceptual reason this works is the closer I get to any differentiable function, it gets more and more and more linear. And the example I have is the Earth, right? If you are a flat earther, keep that shit to yourself. And also, thank God you're in college. There's a hope for you, right? If you're offended by that, give a shit. Stop it. We got rid of that shit a long time ago. Stop it. Now, sorry. We're on the Earth. The Earth is obviously curved. Why does it seem flat to us?
It's so big.
Because we're so damn close to it, right? So if I have a circle and I zoom really far into anything, it's going to end up looking linear. Anything that's differentiable, if I go in far enough, it starts to look linear. Oh, now it's a straight line. That's the whole idea of tangent lines. They follow the curve exactly right at the point. And then they kind of stay close for a while. But if you get too far away from that point, just like we were saying a second ago, if I get too far away, from what I build it around, of course the tangent line doesn't necessarily follow the function anymore, right? That function's gone on and done its own shit. The tangent line, I can only go straight. This function's like, oh, it's too bad, right? Wiggling away. Damn function. So what do I get here? What is f of 0?
1.
1. What is f prime of x? Oh boy. Let me make this 1 minus x to the negative 1.
Negative. or
Negative 1, 1 minus x to the
Negative 2.
negative 2 times
Negative 1.
negative 1. Okay. So what's f prime of 0? 1 to the negative 2, which is 1. So I get a linear approximation of 1 plus x. So this is why I need you to remember a linear approximation, because fundamentally all Taylor polynomials are doing is going further. I really want this to make sense. So, of course I'm not getting any of this.
You're good so far.
So if I do a linear approximation, that immediately sucks, because the function I've got curves away from it. In fact, let's make it a function, Jeff. Circle's not a function, buddy. There we go. Look at you go. Okay. So if I'm trying to approximate here, a straight line sucks very quickly. So if I don't just match the value and the slope, what if I match the curvature? What involves the curvature? What derivative discusses the curvature?
Oh, the second derivative.
Second derivative, right? And of course the higher derivative is also to the, but concavity, for example. So if I match the concavity, if I throw in another term that we're going to see how it's related to the second derivative, it will make things better. So if I make, instead of a straight line, if I make something that curves through there, it's able to hug the original function more. It can stay next to it longer. Does that make sense? Right? Okay. If you want to cover something and all you have is this flat thing, are you going to be able to like cover? No, you want to be able to curve it around the thing, right? Yes.
Is that related to like when you have like points of data and you're trying to like fit the line? You need to like
Yeah.
add more degrees to the function. So like it's,
Yes. So you can do like linear fit,
Yeah.
right? Correlation, and then you do quadratic correlation and cubic correlation, and yeah, and go insane, right? So if you do, yes, that's exactly what's happening. And of course, the higher the degree gets, the more the function's able to follow what's going on. Really, this is so freaking cool. So the rest of you guys, if you remember a linear approximation, you can see Taylor approximation is just going to do add more terms, because a straight line sucks for approximating something that's curvy. That only makes sense, right? Okay, so let's do something else. So all that, hopefully I circled this thing enough, right? So there's the linear approximation. This just makes it better, adds more terms related to the curvature of it through that point. Okay, so let's do this. Somebody help me out. Well, we should know this. What is what if I let x equal 1/10? What is 1 over 1 minus 1/10? 1 over 9 tenths? 10 ninths, yeah. I like it. I like it. Which is 1.1 forever. Okay, great. What do I get on this side if I let x equal 1/10? I get 1. That's my first level. That's my 0th level approximation is 1. That's already pretty good, yeah?
Yeah.
Yeah, it's pretty good. Plus 1/10. Well, that's 1.1, isn't it? Holy shit. But this is 1.1 forever, yes? And what's 1/10 squared? Yeah, there, Jeff. 0.01. 1.11. And then it keeps going forever. So the further I go, the closer my approximation gets to the actual answer. I like this example because it's very obvious. How do I get here? Well, I keep adding 1 in the next decimal place down. That's exactly what's going to happen as I keep going. Okay, maybe. What was the radius convergence? It was -1 to 1, right? Okay, let's try, I don't even know what's gonna happen here to be honest, but let's see what happens. What if I let x equal 2? This becomes
-1.
-1. If x is 2 here, this is 1 plus 2 plus 2 squared. Is that getting closer to -1?
No.
Okay.
So
I
for
really want you to
values-
see the difference. There are certain values of x for which the polynomial works, period. Not makes it that, no, just works. If I choose something outside of the interval of convergence, it's gonna completely blow the shit up. Right? It's just not gonna, I don't care how far you go, it's actually gonna get worse the further you go.
Values 1 and greater.
Huh?
Values 1 and greater.
The value just won't home in on the actual answer.
Oh, right, the range is values
Oh
1
yeah,
and
yeah, so
greater,
if you pick something outside of the interval of convergence,
which is -1.
-1 to 1 for this one, we showed that earlier. So is everybody cool with that?
Mhm.
You must pick a value of x that's inside the radius of the interval of convergence, or else this is not even true at all, period. If you pick a value close to the number you built it around, in this case you built it around 0, right? Then you might not have to go out as far to get a good approximation. Same as always, same as it used to be. If I have a value that's close to what I built it around, then there hasn't been enough time for the function to get away from my approximation. So if I put in here 0.9, isn't that really close to the edge?
Mhm.
Let's see what happens. I like this. This is nice and concrete. So if x is 0.9, what is this?
1 over 0.1.
Which is 10, right?
Yep.
Okay, so let's see. 1, the very first element's 1. Is that close to what the real answer is? Shit! And then I add 0.9.
Uh-oh.
Is that close to 10?
We're getting there.
Getting there, because now I'm at 1.9. And then I add 0.9 squared, right? So 0.81.
Uh-huh.
So now I'm at 1.9 plus 0.81 is 2.71.
1 step at a time.
You guys kind of see what I'm saying? It's gonna take a hell of a lot longer now, because I picked a number that the polynomial will work for. It's just far away from the actual point I used to construct it. Do you see the two different things happening here? So if you choose a value that's outside the interval, I don't care how far you go, it ain't never gonna work. It just ain't gonna work. If you pick something inside the interval, the closer that value is to what you built it around, the quicker this thing will get close to this. This is gonna take a while, all right? This is gonna take a while because every time I do this, it's getting smaller itself, and it's gotta build its way up to 10. When will this equal 10? Exactly.
At
Infinity.
infinity.
At infinity. When you get x to the t, limit as t goes to infinity. Can't do x to infinity. I don't know if you guys are really with me. Are you guys sort of with me?
Mhm.
So again, it's got to be within the interval of convergence for the polynomial to work at all. So if you're in there, the closer you are to the thing you built it around, the better and quicker the approximation gets. Something I love it. When I look around, I always love it when I look around. I got people either looking at me or people going, like this, like, what the shit this guy's saying? Looking at me. I don't know. Hopeful. Okay. So I really want to spend the rest of the time showing you this. So I'm done. No, I'm joking. We're going to construct what those are to make this fit a given function. So get ready. We are going to. So guess which function I'm going to use?
1 over 1 minus x.
No.
X plus 1.
No.
X
I'm going to
squared.
use f of x. Yeah, I'm the math guy. I'm going to use. That's the function I'm going to use, f of x. And what I want to do is I want this to equal this polynomial. Let me do it around 0 just to make things better for right now. Let's make a equal 0. Stay with me. Let's just make A 0. I can make A whatever I need it to be. I'm gonna let it be 0 for right now. Okay. So what would this become? This would be C0 plus C1x. Are you guys with me?
Does that mean we have to change like from n equals 1 to infinity to n equals 0 to infinity?
Say again? Sorry?
You have it set at n equals 1 to infinity. Would that, like, because you made, no?
I'm sorry? So that just means this goes forever.
I know, but I'm saying, do we have to change it from n equals 1 to n
Oh,
equals
0,
0?
0, 0. I don't know if that's what you're saying. It should be 0.
Yeah.
Okay, thank you. Yeah. It's kind of funny that we get so used to using 1 and then they switch it up to 0. I really want you to understand what I'm doing right now. What I'm doing, I could put a specific function here, but then we'd have to do what I'm about to do every damn time. I'd rather do it for every function that exists. Develop a method, and then I can just plug shit in. Given any, I don't have to do the whole damn process every damn time. Where else have we done that in mathematics? Everywhere! Everywhere we've done that. Right? We could have, all right, Jeff, no, but there's no time. There's no time for your normal tangent shit. Okay. So, how do I do this? So, what is f of 0 from this? C 0. Because then every other thing is going to be 0, correct? Okay, so let me do this. Let me see how I can do this best. So f of 0 is C 0. What is f prime of x? Don't give it. It's all right. X is gone, right?
C1 plus
C1 plus,
2 C2x
right? This is not difficult, is it?
plus 3 C3x squared, so on and so forth.
Right? You guys with me? So what is f prime of 0?
Nothing.
No, come on. Oh.
C,
C1.
C1. You guys,
Nothing.
is everybody with me?
Yeah.
What I'm doing is I'm saying, okay, given a function, I want it to equal this polynomial. That's what I want to have happen. So this is how we do that. I've got to figure out what each of these things are in order to get this to work. So C0 obviously has to be whatever F0 is. C1, because of this, has to be whatever f prime of 0 is. So now I'm fitting. I have made my polynomial agree with the function at that point. I've made my polynomial have the same slope at that point, right? And now I'm going to continue the concavity, and then, I don't know if you guys know, well, the next one, if you talk about kinematics, you've got position, velocity, acceleration. Does anyone know the next one? Jerk, right? Which is very much like my first car. You press on the gas, it would go, maybe. What is the second derivative of this?
2C2.
2C2, right? That dies. They're just derivatives. This is awesome. Plus, yeah, they're squared. Plus 12C4x squared. Blah, blah, blah. So what is f double prime of 0? 2C2. So what is C2? Over 2. We are developing what this has to be given a specific function. That's what we're doing. And remember when we first looked at power series, I talked about the fact that these can be constructed. I can kind of make them up out of nowhere. N over n plus 1 times n factorial, just make it up. But this is a specific way to create the CNs. So they accomplish something instead of just making a problem for you guys to do. So let's see. Guess what I'm going to do now?
Third.
Shit. So what do I get?
2.
That's dead, right? That's the constant.
Yeah.
Yes? 6C3.
Plus 24 C4.
Now what I should have been doing, let me see, darn it, John. Let's do this. I should have been doing this. The nth term, right? So real quick, if I do the nth derivative, isn't that n, I'm sorry, the first derivative, n cn x to the n minus 1? Right. You with me? And then the next derivative would have been n times n minus 1 cn to the x n minus 2. And then here it would have been n minus 1, n minus 2, cn x to the n minus 3. So you can kind of, you should have seen by these numbers, at this point 2, 6, 24, that should maybe sound familiar? Maybe? No? Have you not done enough problems yet? Okay. What is f triple prime? A 0?
20.
No?
6.
You make x 0, this is dead. Everything's dead
Six.
except 63.
Sorry.
So C3 equals f triple prime of 0 over 6, which we can now identify as, anybody? Anybody? What did I do to 2 to get to 6? Aren't I gonna get 24 next? What do I do to 6 to get to 24? Multiply by 4. So isn't this factorial? Isn't this f double prime 0 over 2 factorial? Isn't this f prime of 0 over 1 factorial? Isn't this? Okay, Jeff. We talking about 0 factorial, right? It's 1? Okay, good.
Yeah.
So yeah, over, what is it, Jacob? 3 factorial. So what will you think, what is Cn equal to?
F over f of 0 over n factorial.
Yeah, here's the thing. I don't know if you remember what to do with that when you get beyond 3. We just start putting a little number up there.
Yeah.
So this will be f, the nth derivative of f at 0,
Oh, okay.
divided by
N factorial.
n factorial. That's what Cn is. I desperately want you to understand what just happened. So we started with the dream. We said, okay, given a function, I want it to look like a polynomial, please. And we're like, okay, if you want to do that, you got to do this shit. Right? I've got to figure out what these are. What's the only thing I know? What's the only thing I have been given is what the function is. So these have to be related to the function I was given. It's the only thing I know. So have I gotten to a point where I know what all the coefficients are dependent on the function I was given? Yes, totally. So what does that mean, Jeff? I don't know. Oh yeah. So, let me summarize. And by the way, just to remind you guys, on the back of your 11.8 paper is your 11.10 paper, which is this Taylor series stuff. Okay, so let's collect what we've got here.
What is 11.9? I mean, no. This is
11.9 was just power series, derivatives, and integrals.
Okay.
Yeah.
Man, you move so fast.
Alright, so what do we got? We got this. Given f of x, we can construct this polynomial. Maybe I should have used a, that's too late now, Jeff. Or yeah, so then I can say f of x is approximately, or no, it isn't approximately, it equals f of a plus f prime of a over, well, that'll just be f prime of a over 1 factorial. X minus a plus,
Can we make sure filter's on?
plus so I think at the very top of the paper I've got like an nth degree Taylor polynomial. Yes. So I kind of stop there. That's an nth degree Taylor polynomial. So just like when you did linear approximation and you're given an f of x, and you said it was approximately f of a plus f prime of a times x minus a. That's what linear approximation was. Our polynomial sucked because it was only a first degree. At the time, it was fantastic. We just couldn't get very far away from what we built it around, or else they'd go to shit pretty quickly. Now we've got this, we can construct an nth degree Taylor polynomial, And this is just in general if a is anything, not just 0. Okay. And then the actual series would look like, oh yeah, they're doing their,
Just take a.
it's the forensics next door, they're doing their photographs.
Those guys
That
are
was
weird.
like a muzzle flash.
Whoa.
So let's do an actual example. Right. We've had some theory for way too long here, Jeff. Let's do an actual concrete example. Please, dear God.
Amen.
So let's do, yeah, I don't want to do that one. Let's do this one. Let's do sine.
Oh.
Let's do the
Yeah, like not even not even a chance.
All right, let's just build it around 0 first. So let me give you one more word. Taylor was the guy who created this at approximately the same time in the world. And approximately the same time back then was within the same decade, because they didn't have the Instagrams and stuff to get them. They didn't like get on TikTok and go, hey, my fellow math people, look what I've invented. They didn't have that shit. So it took forever for the word to get out. So in the same time, there's another guy, Maclaurin, who created a series where A was nothing but 0. So this is generally a Taylor series. When you make A 0, that is called a Maclaurin series, but it's just a special case of Taylor. We just wanted to give both of them props. Okay. So given this, I want to build Taylor series. Let's say Maclaurin. Let's say
When was this like invented?
Oh geez, 1700s, 1600s.
I don't think they mind if you
You have
give
to look it
props.
back up on that little time frame I've got. Is it MAC? I always forget. MAC. I think it's MAC.
Like the car. Like the car.
Yeah. Given f of x equals sin x, let's build a Maclaurin series. All that means is a is 0. So what you do is you build the coefficients, right? So let's see. F of x is sin x. What's f prime?
Cosine.
Cosine x. What's f double prime? Negative sin x. F triple prime? Negative cosine x. So
Very
forth, right?
monotonous.
You with me? Yeah, exactly. It's just gonna keep going. Okay. So what is f of 0? I need to know what that is.
0.
Yeah, 0. What's f prime of 0?
1.
Yeah, 1. Right. What's f double prime of 0?
0 again.
0. What's f double prime of 0? I'm stripping
Negative 1.
Negative 1.
And then that loops.
So you can pretty much guess what's happening here. What would f 4 0? What's the fourth root of
0.
Zero. Fifth root of
1.
1. Okay, okay. Get the idea. So let's build the first few terms of this series. So what we have here is sin x equals f of 0, 0. F prime of 0 times x minus 0, so I get x. All right, we're not done yet, right? But do you guys remember? As x approaches 0, doesn't sine of x become approximately x? I don't know if you guys remember that. Do you guys remember limit x goes to 0, sine x over x equals 1? Maybe? You can do L'Hopital's now, and of course, before you knew L'Hopital's, you actually talked about this. Okay, so that what this says is when x gets small, sine x is approximately x. That's exactly what I've got so far. But it only works if x is really close to 0. So if I add a few more terms, it gets better. Where am I at? So this one. So every other one is 0. So this one will be 0. So now I need the next one, which will be, so I can kind of, so it'll be f triple prime of a over 3 factorial cubed, right? And of course I can always reference this. I need the third derivative of f at a, which is negative 1, over 3 factorial, which is 6, times x to the third, Cool, so far.
And then back to addition.
Right, and then the next one is 0, and then the next one after that, right? So we're at 1, 0, negative 1, 0, 1. We're at the fifth one now, right? 5. So I need the fifth derivative of f at 0 is 1 over 5 factorial.
120.
120.
X
X to the fifth. Minus dot dot dot.
Pretty cool.
So is that enough? Can you just finish there?
Depends on the question.
Okay.
So can we find
Building
a-
the Maclaurin series is that though, right?
This is the Maclaurin. This is the beginning of the Maclaurin series. Yes.
So how? Oh, it would tell you how many terms you need to go to. In a
It
question
could.
like that.
It could tell you how many terms. It could say approximate it to the fifth decimal place, which means you keep going until you get that decimal place not to change. Right?
Wouldn't what you had for X though affect the number, or would you just use?
Sorry? So one thing is we definitely still need to figure out what the radius, what the interval of convergence is for this. Which
Right.
means, can we write this in this closed form, which I erased, of course? Can I write this in this form? Yeah, sure. Cn x to the. Can I figure out what this is? Right, you can't always. Sometimes you can. So let's look at just the numbers. Let's look at just the coefficients. It's 1. Don't worry about the negative part. We can throw that in. Is that cool? 1, 1/6, 1 over 120. I might have to do another one just to see what it is. What would another one be?
So can you just plug in like any value?
Sorry?
Could I just plug in like any value and see how long it takes for the Maclaurin series to make it like to the specific number of decimals that I wanted, or?
Yeah, so if they say approximate sine of, 0.1, correct to 5 decimal places.
Okay.
Then you put 0.1 minus 1, and you keep going until your results stop changing in the 6th decimal place. Then you're certain that the first 5 are right.
Okay.
Because what's happening to every term as they go into this? Aren't they all getting smaller, smaller, and smaller? Which means it's affecting the result less and less, further and further out. So if they want me to be correct to the first 5 decimal places, I keep going until the first 6 don't change. Then I'm certain the first 5 don't change.
Is it 1 over 2n minus 1 factorial?
All right, let's see. I love it. You started thinking about this. So we got like 1 over 1, 1 over 6, 1 over 120. We're trying to figure out, and I was going to see if we needed another term, but what's your guess?
1 over 2n minus 1 factorial.
2n minus 1 factorial. Yeah, because it's the every odd one.
Yeah.
Right? Beautiful.
We've seen that a bunch of times already.
Yeah. So this will be, let's check it. If n is, what do I got? Well, be careful. Yeah, if n is 0, let's see. So we should make this plus 1. If n is 0, then I get 1 over 1, right?
Oh, because we start at n equals 0. Oh no, we start at n equals 1 though.
Oh yeah, I put 1 there. Keep forgetting. It's fine.
Oh, okay. So yeah, then it would be plus 1.
You got it. That was my fault. And if n is 1, then I get 3 factorial, which is this.
6.
And we kind of know that it's going to be an odd number because it's every odd element that works.
Yeah.
So, cool. Let me show you this. Bum, bum, bum. You can do this process for almost any function. It's almost guaranteed if I put that up, I'm going to need it.
So then with the Maclaurin series, are we like looking for like a C of n like that?
You're constructing your CNs.
Okay.
So it's like what I said before, I could just kind of make CN up
Yeah.
to make a problem for you guys to look at, a power series problem for you to look at. Or, and this is not the only process that helps us construct CNs to do a specific thing, but this is one of the more well-known ones. We are constructing, so we still have a power series. We're just constructing these to be specific things. I want them to accomplish specific things.
Yeah.
I want them to match, to make this polynomial end up approximating some given function correctly. So here is, holy crap, here is something you cannot see. All right.
Still kind of.
That's still rough, yeah.
All right. There. Give me a second. Where's that? I like that the focus says AF. Focused AF.
That's better.
Okay. So the very first one, of course, is the first one we looked at. There's sine x, the one we just did, right? There's your 2n plus 1 factorial. I love it. And then there's more, there's cosine. And look at this. Do you see how cosine and sine sort of fill each other in a bit? You see it?
Yeah.
Do you remember that shirt I wear sometimes? It says e to the I pi plus 1 equals 0. We're almost there. We're going to prove the hell out of that thing. So we're almost there. I'm so excited. Because look at e to the x. Look at e to the x. Compare e to the x, that polynomial, to sine and cosine.
Very similar.
Oh, it's a combination.
Yeah. Okay. So somehow they work together in ways that we would never have guessed before we looked at converting these into polynomials.
Is this like
So
constructive
is
synergy?
is the I how you get the signs of that?
Yes. I love it. Because you can, if you, yeah, we'll get there. So you already, I love it. It gets really blurry, I'm sorry. There's your arctangent. This is page 768 in the book, I think it is. Yeah. Oh, wow. A little better? No, go fine.
Wait, are arctangent and sine the same thing? Wait, what?
No.
X?
Look at it.
Factorial.
Where am I?
Oh, factorial.
Tangent and sine. Inverse tangent? Oh, I see.
Yeah.
Yeah, inverse tangent is missing the factorial. Yeah. Which is kind of funky. Come on, book. That last one is called the binomial series. And I don't know how many of you guys know what this is. Oh. It's from probability. It's where you most often see it. It's called combinatorics. It's the k choose n. But it basically just breaks out like this. K times k minus 1 over 2, so forth forever.
So is that a series that you can use in stats?
NPR, National Public Radio. Yeah. Yeah, so it tells me you took statistics. Yeah. But this is the combination, this is C. This is the combinations, yeah. Okay. And each one of these things, you can develop the same way we just did there. So the process doesn't change. The process is a given. And the really beautiful thing, okay, I really want you guys to get this, and then I'll let us out here. Let's see, then I have some choices to make. The really nice thing about the form of this is everything kind of matches. So f of x equals f of a plus prime of a over 1. So this is like over 0 factorial, 1 factorial. So first derivative, 1 factorial. Yeah, there, Jeff. First power. 0 with derivative, 0 factorial, 0 with power. Everything matches. Plus second derivative, 2 factorial, second power. I mean, it's just kind of amazing. And then, just keep going. 3, 3, 3. Blah, 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 blah. Will this work for every function in existence? No. It will only work if you do the nth Taylor series, nth Taylor polynomial, I'm sorry. And then you're going to have, let's see if this makes any sense. You would have a remainder term, right?
Mm-hmm.
If you stop it somewhere, it's not going to be perfect.
What's that?
Oh,
They're gonna actually take pictures of a real person down there.
They locked somebody in there, they just woke up, so. And the only ones that works for is if the limit of this remainder goes to 0. And that's not true for every function. You might be able to imagine that the functions that don't work are exceptionally weird. Normally the functions that things break down for are really strange.
So probably something we're not gonna deal with.
So most functions we've worked with will have Taylor series representations. Okay.
Could you give us an example of one that doesn't? Like, what's a weird function?
Oh geez, off the top of my head, like, there's some really lame ones that are just piecewise functions that break down for all these reasons. I don't know. Off the top of my head, I don't know. I should have come ready, but I know they're out there. I've seen them, but they're kind of weird. Oh, guys, I'm really sorry. I've kept you so long. I've got the practice test, but I wanted
Yeah,
to
that would be
see.
nice.
When's our next?
Monday.
Yeah. Gotta have the practice test.
Yeah, me too.
Okay.
Can you give us like the real test or?
Let's see it.
The real test?
The real test, right? Like I haven't.
Dude, I
You
gotta
just
take
post it
one.
on
Is this quiz ones?
Canvas. if you don't
Yeah,
have it.
shoot. I think I printed them out and left them up on
Is
the
these
printer.
quiz ones? Make it worse.
What?
Sounds like something I would do.
It was like
No,
taking
no,
for a
post
reason.
the
It
post
took
the
you, like,
fake
the whole
test on
5
Canvas.
Post the real test.
Post it all on Canvas. We'll do both.
Yeah, I'll do that. So I'll send you an email when I do that.
Okay.
I just forgot to bring them with me.
I'm still picking up.
Say again?
If it doesn't-
That was scary.